Okay, good morning, everyone. I'm Peter Knapp. I'm a postdoc at UW, if you don't know me already. So we'll try to stay on time so we don't go into our shakeout. The morning session's called The Great Glacier Conveyor, a nod to recently passed luminaries, John Nye and Wally Broecker. And let's see, I think to keep time, I'll have a timer, and then when it gets to be 2 minutes, I'll just stand up and start lurking respectfully. So first speaker today is Lindsay Prothro, so let's take it away.
Right, thank you. That was really exciting morning so far. Thank you all for being here bright and early. Today I'm going to be talking about the role of subglacial meltwater in grounding line retreat. And I'm going to be mostly focusing on the Marguerite Bay system, but this project is actually motivated by the Thwaites Pine Island Bay system. Because there in particular there's a really urgent need to understand all of the potential forcings of ice sheet instability and also the timescales over which those processes operate. Here's a look at Thwaites and Pine Island Bay. This is one of the most vulnerable regions of Antarctica, as we all know, and probably the biggest threat to the system that we can pretty much all agree on is undermelting from warm currents impinging onto the continental shelf. Yes, that's causing unprecedented rates of change, but it's also important to understand other possible contributors to instability. And so one thing that we can take a look at is, we know that there is active movement of meltwater underneath the ice sheets today, and there also is underneath Thwaites and underneath Pine Island as well. There's been actually documented sediment plumes emanating from beneath the grounding line and also being deposited beneath the ice tongue. And this is believed to be from subglacial meltwater. And so the issue here is this is all happening now. It's not the complete story. We're not completely sure how it connects with grounding line retreat because it's happening now. So as a geologist, I want to look back into the paleo record and see if there's some analog for this system that we can find there that can maybe tell us more about how all of this is linked up. And as a sedimentologist, I want to know, is there a sedimentological marker of impending change? And so the first thing we can do is just take a look at the same system. So the continental shelf that has already been deglaciated in the Amundsen Sea, we can see there a nice extensive network of basins and channels connecting those basins, suggesting that meltwater was flowing between those basins at some point. This could have happened during any time in glacial history because it's carved into bedrock, so we don't really know how old this system is. But there have been some, that's blurry. There have been some sedimentological studies on the continental shelf looking at the sediment cores, and there's a unit right at the top of several of the cores in the Amundsen Sea that has been interpreted as a meltwater plume deposit. And this facies is very different from other facies in that it's relatively well sorted silts compared to what a lot of other glacial sediments look like, which are very unsorted. And there's a fairly consistent 10 micron mode to this sediment. Don't really see any pebbles in it. Very few siliceous biogenics in there. So not a lot of diatoms from open water, or it could just be rapid deposition of sediment. And so this has been interpreted as a meltwater plumite. But the thing is, this has been dated. It's actually modern. So this is sediment that's being laid down now as a result of that currently active meltwater system underneath Pine Island Glacier. So we can try to look a little further back in time. And so we have some evidence in the Ross Sea as well of past meltwater activity on the deglaciated continental shelf. So we have mapped some very nice channels here. And seaward of these channels, we've found in 9 cores that very same sort of sediment that we see in the Amundsen Sea. A very nice, relatively well-sorted grain size distribution with a 10 micron mode. And I forgot to mention earlier that this mode actually lines up with the mode of till. So till also in both of these areas has had a 10 micron mode, but it's much more widely distributed in grain sizes. And so that's one of the reasons why we think it's just a sorted version of till. The sediment was derived subglacially and then emanated at the grounding line to be deposited in front. And here again you can see sort of the very smooth nature of that facies. There are no pebbles, it is just silt. And in the Ross Sea, we've dated these cores as well, and it was very rapid deposition. There aren't even any foraminifera in there. It got deposited very quickly. So we're convinced that there as well, this was a meltwater plumite deposit. But the difference between this and the Thwaites system is that this is a sedimentary substrate. It's not the same sort of channel system. It's not really a good analog to Thwaites and Pine Island Bay. So an alternative is looking at Marguerite Bay. So Marguerite Bay has been deglaciated for some time, and it has the same sort of substrate that Thwaites and Pine Island Bay has. It's very rugged bedrock on the intercontinental shelf, smooth sedimentary substrate on the outer continental shelf. We know this from several seismic lines that were taken a couple decades ago from there. And you can see, zooming in right there, you can see a nice little network of anastomosing channels right here. You can see some potential basins where water may have ponded underneath the ice. And so this could potentially be a really nice place to look to see what Thwaites might do in the future, because we can get a complete story here. And so we've also revisited some cores that were taken in the late 80s, and we've run some grain size analysis on them. And we see a little bit messier, but very similar sort of grain size distribution in sediments that were previously suspected to be meltwater deposits, but hadn't really been analyzed in detail. And so here again, we see fairly well-sorted sediments, 10 micron mode again, extremely smooth, no silicious material, no pebbles. So here again, we think we're seeing potential meltwater deposits. And if we look at the spatial distribution of these, all of these yellow marks here are where we have found that facies and also the thickness of it. And what we see is that facies is primarily restricted to the intercontinental shelf. It doesn't make it out to the outer continental shelf where we have this 4 deep end slope. And so we're thinking that this may mean that this sediment was expelled at the grounding line at either very high concentrations or very high velocities. So it remained at low levels and didn't make it all the way out. So how does this fit into the actual retreat history? We've gotten a few more dates from the previous reconstruction that was done in 2014. This was based on ages that were collected in the 80s and 90s, and you needed to have a lot of material to get a good carbonate age back then, but technology has improved, so we were able to get several more ages and add some better constraints to this. And so on the left, I'm showing the previous reconstruction. On the right is mine. The dark gray is grounded ice. The light gray is ice shelf. And so there's a lot of dotted lines on the left. But we first start to get some really solid constraints around 14,000 years ago. We have some more around 13,000, and it keeps on retreating. Sorry, running out of time. But the point is, the most significant retreat that we're seeing happens between 13 and 10,000 years ago. Still a bit different from the previous reconstruction. But yeah, so most of the retreat happens between 13 and 10. Also, we have about 20 dates from that meltwater deposit, and they are all also falling in that 13 to 10,000 year range. So it seems that it's very strongly linked to retreat. And given that WAIS Island is putting out a lot of meltwater deposits right now, it looks as though meltwater may be a potential herald of major ice sheet retreat. So it's something to look out for, and I am very much out of time, I believe. So I will turn it over to someone else.
Cool, thanks. Next up, we have Perry Spector. I think, in general, we'll be holding questions, except for the very burning of most questions for the discussion at the end.
All right, good morning. I'm Perry Spector. I'm a postdoc at the Berkeley Geochronology Center. I'm going to be talking today about ice thickness changes through the last deglaciation, both at the divide of the Western Arctic ice sheet as well as on the flank.
Can you make sure you use the mic, Perry?
Yep, I'll try to.
You can pull it out and hold.
Okay. Okay, so the expectation is that ice thickness changes in West Antarctica will largely have been due to competition between two main processes. One, dynamic thinning. So as the grounding line retreats, dynamic thinning will propagate upstream. And to some extent, that will be opposed by the increase in the accumulation rate, which, at least at the WAIS Divide ice core site, we know roughly doubled between about 18 and 15,000 years ago. Most of our knowledge of ice thickness changes come from exposure dating studies from sites along the ice sheet margin, and from these studies, we see monotonic thinning through the last deglaciation that's presumably linked to retreat of grounded ice downstream. In contrast, we know very little about thickness changes in the interior. The few constraints we have come from work by Robert Ackert. It's been hypothesized that in contrast to the margin, where we see monotonic thinning, the divide actually thickened early in the deglaciation due to the rise in snowfall, and then only thinned later once dynamic thinning caught up and became the dominant process. So I'm going to show results from the Whitmore Mountains, which are actually consistent with that hypothesis, and also results from the Pyrrhot Hills, which are midway between ground line divide and the Waddell sector. So going first to the Pyrrhot Hills. Sorry, it's a little bit blurry. But based on glacial deposits and cosmogenic nuclide exposure age dates on those from Berkeley and Penn, there's evidence that during the last ice age, ice reached 320 meters above its present level here in the Waddell Sea. These are exposure ages, so time going to the left, this is the sample elevation. These are from samples shown by these yellow dots. Just to keep this quick, the way to interpret a plot like this is that the youngest ages at a given elevation represent our best estimate of ice thinning here. So here at the Pyrrhot Hills, we see that the high span was maintained until about 14,000 years ago. Subsequent thinning is only constrained by a couple samples. We see thinning through the Holocene, modern ice levels established 4,000 years ago or more recently. Although this is quite thin, it's actually similar to records from other sites in the southern Woodelsey embayment, the Heritage Range in red and the Pensacola Mountains in blue, sites where they're able to collect many more samples. So again, kind of following the left-hand edge of these points, you see rapid thinning of several hundred meters in the mid-Holocene between about 7,000 and 4,000 years ago. Just for comparison, this is the accumulation rate record from WAIS Divide. You see this doubling roughly of snowfall between 18 and 15,000 years ago. At the time when rapid thinning is occurring in the southern Woodelsey embayment, accumulation rates aren't varying a ton. They're going up a little bit. So presumably this monotonic thinning here is linked to retreat of grounded ice downstream of the Waddell. Going out to the divide, this is the Whitmore Mountains. We found no fresh glacial deposits here. That's not surprising. This is actually on the divide, so where could debris be coming from? We collected this elevation transect of bedrock surfaces, and so what I'm showing now is measurements of cosmogenic C14, so C14 produced in situ in quartz. Okay, so the way that this works, C14 is very short-lived, half-life of about 5,700 years, and so if you have a surface that's continuously exposed for 30,000 years or so, C14 will increase to some point of saturation where the production rate equals the decay rate. The concentration is no longer time-dependent. If you have a surface that is at saturation and is covered by thick snow or by ice, decay will dominate, concentration will decrease. If it's re-exposed, C14 will grow in again. That's basically how this works. These are our results. These correspond to these samples. Elevation is on the y-axis, C14 concentration on the x. This gray band here represents saturation, which is a function of elevation. So the main finding is that we have 4 samples here that have C14 concentrations indistinguishable from saturation. That indicates that these surfaces have been continuously exposed for about 30,000 years or longer. So the lowest elevation saturated surface places an upper limit on the highest end of the WAIS here at the divide during the last 30,000 years. And that's at about 190 meters above the modern ice surface. You'll notice that we have surfaces with concentrations below saturation, both above and below that high stand level. Many of our samples were collected relatively near to present-day snowfields and to this summit ice cap, and so it's definitely possible that these samples could have been covered in the past, and so that's our interpretation for these upper samples that are not C14 saturated. For these lower ones, it's more ambiguous. They could have been covered by expanded local snowfields or by a thicker WAIS here, or by some combination of that. So although we can't rule out the possibility that ice actually wasn't higher at all during the last 30,000 years, that's pretty unlikely based on especially work by Robert Ackert at the Ohio Range, where there's evidence for ice more than 100 meters thicker than present. So we can go a little bit further if we just look at the 2 lowest elevation samples that are collected very close to the modern ice surface and have similar C14 concentrations. So these provide some constraint on basically when ice became thicker than present and when it thinned to its modern day level, and that's represented by this plot here, where the y-axis is when they were covered, and the x-axis is when they were re-exposed, which is more or less analogous to when ice became thicker than present at the Whitmores and when it became thin to its present day level. So this gray band represents the set of all possible scenarios of thickening and thinning here at the Whitmores. This area to the left of it in white is actually forbidden because these scenarios underpredict the C14 concentration that we measure. They would predict something over here. We can't actually rule out scenarios that overpredict the concentrations we measured because of the possibility that snow cover could account for some of the undersaturation. So basically, this whole area in gray are the scenarios of possible times when the ice became thicker than present and when it thinned to its present day level. We can consider, though, that there are other, the broader ice sheet context of and what we know about the timing of other changes. The most useful constraint is that because dynamic thinning propagates upstream, sites downstream would have experienced thinning, prior to the divide. The most useful constraints come from sites that are closest to the flow lines that descend on either side of the divide from the Whitmores, that being these sites that's here, and also from Lower Reedy Glacier. So based on those constraints, I'll just try to keep this quick, that limits the number of possible scenarios to this area in darker gray. And just to summarize what that means, because this plot I know is a little bit complicated, what it means is that thicker than present ice cover at the divide, or at least at the Whitmores, was relatively brief and it was relatively recent. So a period of no more than 8,000 years of cover within the past 15,000 years. So basically, this hypothesis, or our results are consistent with the hypothesis that that during the LGM ice levels were either lower than present or the same as present, and then thickened in response to increases in snowfall, and then thinning occurred only once dynamic thinning caught up and became the dominant process here. So that seems consistent with what we know about accumulation rate changes in West Antarctica. And then, so the only other thing that I'll add is, I don't think I have time to go into this in detail, but we can basically use these constraints from the Whitmores, from the Pure Hills, also from other places, to evaluate numerical ice sheet models that simulate the evolution of the ice sheet over the last deglaciation. Most models, recently published ones, do relatively poorly. The ones that appear to do the best, at least at these two sites, are recent ones by David Pollard. And I think I'm basically out of time, so I'll wrap it up there. Thanks.
I'd really much like to move around to if I can walk and chew gum at the same time.
I handed them all out yesterday.
Is the event.
I can grab some poster ones from upstairs. I can do it now.
All right. So I will be talking today about results from a subglacial drilling experiment that we did in the Pure Hills in West Antarctica. And the authors for the talk are cast of thousands, of whom Perry and Trevor and Jeff are here today, and then there are many others. We are living in a world where human activity has already raised greenhouse gas concentrations to effectively Pliocene levels, so welcome to the new Pliocene. And at the moment, there's a great deal of interest in the community in looking back at Pliocene analogs of the ice sheets, looking back at the Pliocene ice sheets to try and use those as analogs for how we might expect the ice sheets to respond in the future. But also interestingly, much of that is being driven by modeling of what the Pliocene and Pleistocene ice sheets may have looked like. And the purpose of this talk is to show you that there are ways to test these models before we come to rely on them heavily for predicting what may come in the future. The tests that I will be talking about today come from drilling into the bed beneath the ice sheet, in this case in the Pure Hills. But what you can do with subglacial drilling and recovery of bedrock from beneath the ice sheet, we have a way to record a great deal of information about whether or not the ice sheet has collapsed and gone away at that particular site where you drilled. And so the tools that we use to do this are, first of all, cosmic ray-produced isotope measurements on the bedrock beneath the ice. It only takes a few meters of ice cover to effectively shut down the production of most of the cosmic ray produced isotope signal. So in effect, a collapse that exposes bedrock, it's like someone came along and painted it red. It's a label that persists for millions of years, allows you to see exposure of that bedrock very distinctively and quite unambiguously had it happened in the past. In addition to this, you can use a technique called optically stimulated luminescence dating to actually tell you the time at which that bedrock surface was last exposed to sunlight. And a third part of the work I'll be talking about involves if you're able to core the ice directly in contact with the bedrock, then there is information also about the timing of last exposure of that rock from the trapped atmospheric gases in the ice in contact with the bedrock. But together, these actually are able to provide you with very clear and unambiguous evidence about whether or not that rock has been exposed in the past. And many of you, of course, will know that this our work is preceded by work, originally measurements done by Kuni Nishizumi on the GIST-2 basal bedrock, which have demonstrated and then repeated by Jörg Schäfer's group that have shown that central Greenland has been exposed in the Pleistocene by loss of most of the Greenland ice sheet. Okay, so we chose to do this at a place called the Pirret Hills. It is hard to see given the, I'm sorry, how do I, there we go, I have to go back two, all right. Yeah, so there are many places where you might do this in West Antarctica, and I direct you to Perry's paper on selecting sites for subglacial drilling. The Pirret Hills are in the Weddellsea catchment here. This panel shows what the ice sheet might have looked like at a during a large deglaciation of the West Antarctic ice sheet, in which case the Pirret Hills become beachfront property here. In a glacial stage, thickening of the ice sheet, the simulation on the right is shown there. And one of our purposes in choosing this site was that if you take that Pirret Hills pixel from David's model and you plot the height or thickness rather of Pirret Hills ice, and then look at the total mass of the West Antarctic ice sheet recorded by the model, then there's a reasonably good correlation between what the Pirret Hills do and what the ice sheet more broadly might have been doing. So that was another motivation for going there. There's a long list of other reasons to go to this particular site. I won't read down this list other than to say that the rock type is suitable both for doing the cosmic isotope measurements we wanted to do, large number of isotopes. The rock is suitable for the luminescence dating that we wanted to do. And our reconnaissance established that erosion rates at this site have been very low in the past, so there's a very well-preserved signal of thicker times when the ice sheet was thicker in the bedrock above the ice sheet. And also, you can see from this lower photograph that weathered rock in the Pirret Hills descends below the ice sheet. So that alone, that simple geologic observation which people have been making since the 1960s, tells you that there have been times in the past when the ice sheet was thinner at the Pirret Hills as well. And so the question then is how much thinner and when? So we did the drilling with IDDO's recently commissioned ASIG, agile, not so agile, sub-ice geology drill. We got it there, it all worked well, but it was a very big logistics effort, which we thank everyone who contributed to that. It's what's called a wireline drilling idea, and it's a magical technique by which you're able to, once you get to the bed, you can extract rock core after rock core up the drill pipe, and you use the drill pipe to contain fluid that circulates the cuttings back to the surface. So this is the principle also behind the ray drill, which Jeff and John Googe have been developing along with. Anyway, let's go on and show you it in action in the Pirret Hills. I'm really going to race through these. Here's the core. We lost our initial hole to a hydrofracture in the basal ice. We have 8 meters of rock core from our second hole, and that was recovered with about 5.5 meters of discontinuous ice from directly above the Here are the cosmogenic isotope results down that bedrock core, so ice above, and then 8 meters of core down here, beryllium-10, aluminum-36, and the ratio. You can learn a lot from this, and I'm sorry, I'll have to race through this because I will not get under 10 minutes if I don't. But what we found is surprisingly low concentrations of cosmetic isotopes, but we are able to say that this surface has been exposed in the past. So the little bend in the profile at the top corresponds to that portion of the cosmic rays that penetrate into the uppermost meter or two of rock when the ice is absent, and that little spologenic profile at the top of the profile there would form with about 60 years of exposure at the present day cosmic ray flux at the peripheral site. I'm really out of time. Okay, so you'll notice it's absent in the aluminum-26. This one decays faster, so the presence in beryllium-10, absence in aluminum-26 tells you this was produced a long time ago. And if it was produced back in the Pliocene, it would be about 200 to 800 years of exposure would produce that. In the Miocene, you can allow for longer exposure. Just to put this in context, had the Pirit Hills experienced the same exposure history as the Greenland ice sheet recorded in that Disk 2 rock, these profiles would be here, and the top, the top of those profiles ends up somewhere up in the next county. A very, very distinctive difference. Okay, so the presence of that tells you also the surface is not eroded since that was accumulated. The ice deeper in the core, below that, is produced by muons, a very penetrating portion of the cosmic radiation that makes it through hundreds of meters of ice and has penetrated into the bedrock. And what's built up below here has been accumulating for more than 3.5 million years, based on the ratio of aluminum-26 to beryllium-10, which is produced at a ratio of 9, but equilibrates at a ratio, as we find it, about 4.5. And you can do something interesting with that because you can then compare the abundance of beryllium-10 in that muon-produced portion of the profile to what you find in statically exposed rock in the unglaciated part of the world. And this portion of the profile would build up under approximately 70 meters of rock, and that's equivalent to about 200 meters of ice cover. So you want to think of that as the average Pleistocene ice cover of this site. It's about 200 meters, something like that. Oh, I keep losing the slide, sorry. And that's about 55 meters thicker than the depth at which we drilled the ice. So on average in the Pleistocene, ice has been thicker at this site over the time average. But we know that during glaciations it gets hundreds of meters thicker, so that must also be balanced by times when it has been thinner in the Pleistocene. It just has not been 150 meters thinner than it is at present. Okay, so very quickly, a luminescence measurement on the top of the core. The luminescence is saturated, and that's the result of being not exposed to sunlight for the last 400,000 years or more. That's consistent with what we get from the other cosmogenic isotope experiments. Jeff measured trapped gases in the 1.5 meters of ice above the bedrock interface. There are many interesting things about this. The basal ice itself is full of helium-4 and argon-40, which are the radioactive decay products of uranium and thorium and potassium in the bedrock, which then diffuse into the basal ice. So you can see that there is excess argon-40 in these profiles. There was excess helium still in the basal ice months after the ice was collected. But the really interesting measurement here is the argon-40 to 36 ratio, and as you move up into the basal ice, the delta argon-40-36, which is the isotope ratio of the atmospheric gas trapped there, is actually negative relative to the present day atmosphere, and looks like that gas was trapped at a time when that ratio was 0.15 per mil less than it was at the present day, and by Mike Bender's calibration of that evolution in the Earth's atmosphere, that would make that basal ice between 2 and 3 million years old. So in drilling into this rock surface, we also stumbled on basal ice that is millions of years old. And is interesting in that sense. So here are my conclusions that very definitively this rock surface has been exposed, but not within the last couple of million years. The average ice cover over that time has been about 200 meters, and that was preceded, as I said, by exposure in Pliocene or earlier. The other thing I want to convince you is that there's loads of information available in subglacial drilling like this, and we really wish we had the second core, because if you take your cores in succession towards the surface, you get vastly more information than from a single core. So I'm going to stop there and let Trevor take it away to tell you further about how we interpret this result.
Thanks, John. I don't know if because Trevor's talk is tied to yours, he might have 2 minutes less now, but.
Okay, good morning, everyone. I'm Trevor Hillebrand. I recently finished up my PhD at the University of Washington, starting a postdoc at Los Alamos on Monday, so I'm currently unaffiliated. So I'm just going to pick up where John left off and talk about some ice sheet modeling I've done. So if you weren't here for John's talk, or if you slept through it, this is the one sentence conclusion, is that ice around the Pirate Hills has not been appreciably thinner, or 150 meters thinner, during the Pleistocene. But of course, this is just one spot on the flank of the Western Antarctic ice sheet with one hole there. So how do we get from this beautiful but small mountain range to something that can tell us about Western Antarctica as a whole? And of course, for that we need a numerical ice sheet model. So I've been using the Penn State ice sheet model, which gave us these lovely and dire predictions of future Western Antarctic ice sheet collapse. I'm exploring, just to keep the ensemble at a reasonable size, I'm exploring just the three warmest interglacials of the Pleistocene. So these are marine isotope stage 5e, which is the last interglacial, stage 11, which is 400,000 years ago, and stage 31, just over 1 million years ago. And I'm running this as a nested configuration, so I run the whole continent at 40 kilometers resolution, and then a high resolution 20 kilometer grid within that to cover West Antarctica. In total, the ensemble is 540 model runs, which is 90 parameter combinations over these 3 time periods at 2 resolutions. I'm only going to talk about the higher resolution simulations today. And it's important to note that we're using this sort of simplified parameterization of climate over the Pleistocene, which just essentially scales recent model simulations of climate to this delta 18O stack. So we're exploring parameter space that has uncertainties on the order of 100 to 1,000% in a lot of these cases. So I'm using 3 different coefficients for ice shelf hydrofracture, this process by which surface melting can break an ice shelf, but I'm including 0. 3 different scalings for sub-ice shelf melt of warm water and going up onto the continental shelf, using a fast and slow rebound time scale, different sort of speed limits on this cliff failure mechanism, also including 0, and then different values for the basal sliding on the modern day seafloor, because we don't have ice velocities there that we can solve an inverse problem for basal traction. Okay, so let's get into results quickly, since I only have 1 minute left already. Okay, so these are each of these interglacial periods. The column here, the black curves are the model data as a whole in terms of ice volume above flotation, and modern is that dashed line. And here in orange, we have the Pirate Hills ice thickness from the model. So you can just see by looking at this, this is the Pirate Hills ice thickness corresponds well with the size of the ice sheet as a whole. We can quantify that using the R squared between those two, so there'd be 90 different dots on all of these. So I've done this as a box plot, and this black vertical bar is the median value. So in a median sense, the Pirate Hills ice thickness contains or predicts 70% of the variance in West Antarctic ice sheet volume. So this is a good place to do this experiment. But if we compare this to our drill depth, So blue here is bed map 2, and red is the Pollard 2016 ice sheet model representation of the Parrot Hills. So subtracting off 150 meters for our drill depth on these dashed lines, there is at least 3 times in the last, or during these interglacials, that this core is predicted to have been exposed significantly for tens of thousands of years. So the takeaway here, model ice thickness of the Parrot Hills is a good predictor of ice sheet volume, but we have this disagreement between the ice sheet model and the isotope results. So let's look at what these interglacials look like. This is a composite, so the median ice thickness between all 90 model runs at the time of minimum ice sheet volume. So you can see we have, during stage 31 and stage 5e, you have appreciably smaller ice sheets than modern, but not the full collapse in the sense of an open seaway through West Antarctica. And stage 11 actually looks quite a bit like the present, but with larger ice shelves. So if we plot up the grounding line for every single model run, you see we do get a few collapses, but just in stage 31. But we should note that to get a collapse in this model representation anyway, we need to increase ice shelf melt, we need to have some amount of hydrofracture and cliff failure, and then we need a slow rebound time scale and a resistive bed over the modern seafloor. This is kind of the most aggressive parameter combination. So obviously many people have modeled West Antarctica sheet collapse, so I'm going to compare this to the Potsdam PISM group, Feldman and Hillebrand. So they found that they forced the ice sheet with moderate melt rates in the Amundsen Sea and then let it evolve. So any forcing between 60 and 200 years led to a complete deglaciation of the West Antarctic marine basins. But here, the Parrot Hills are still quite far from the grounding line because there's no real forcing in the Liddell sector. So we only get 30 meters of thinning at the Parrot Hills, which would obviously not expose our core. But we end up with large ice shelves in the same configuration as today, and then this large ice shelf in central West Antarctica. So I think the takeaway here is that if you don't lose your large ice shelves during deglaciation, we wouldn't see a large drawdown of the Parrot Hills. So Michel Titchelar and company have modeled over the last 800,000 years using the same Penn State ice sheet model, but with an explicit coupled atmosphere and ocean model. So comparing their results to ours, so this is my ensemble. For stage 11, they found an ice sheet similar to mine, and for stage 5e, one much larger. Now, in order to find the thresholds at which the ice sheet would collapse, they ramped up their ocean melting anomaly. They had to increase it by a factor of 5 to get the ice sheet to collapse. And so this is in this panel here, but still no collapse in the last interglacial. So if we look at the ice thickness of the Parrot Hills for these, so the green curve here, apologize if that's hard to see, corresponds to their warm ocean simulation. And that gets down to about the level at which would expose the Parrot Hills bedrock core. But there's no such large drawdown during the last interglacial. Okay, so to wrap this up, ice around the Parrot Hills has not thinned by 150 meters or more in the last few million years. And my modeling shows the ice thickness at the Parrot Hills is a good predictor of the West Antarctic ice sheet volume, but with the caveat that for a large drawdown of the Parrot Hills, it seems that you need to lose the large ice shelves. So taken together, I think this means that if the West Antarctic ice sheet and the ice shelves collapse during an interglacial, we would see a signal in the bedrock core, which we don't. So the scenarios that are consistent with our isotope results, you can have an interglacial that looks like this, or an interglacial that looks like this, but not an interglacial that looks like this. Thank you.
All right, I think Trevor wins a prize for not even having to stand up and remind me he had 2 minutes left. Maybe an extra waste cup for you. So next speaker is Robert Ackert, and then I'll ask, as soon as Robert's done, all of the speakers in the session will come up and we can then ask all of our burning questions. even though we're already eating into our discussion time now.
The green button.
What's that?
The green button. Green line.
Top one. Yeah, great. Okay. Well, I'm fortunate that the previous talks have covered most of the introductory material that I would need to cover, so I can go pretty quickly. I just want to acknowledge my co-workers here, and especially Zach, who made all of the measurements and is responsible for the plots that I'm going to show you today. So, we're really fortunate with the Antarctic ice sheet because of these mountains that come through it in various places that we have a really good handle on what it looked like in the past through these glaciological techniques and exposure dating. And I would say that, at this point, we may have reached the point of diminishing returns for understanding the last glacial maximum to the present. We certainly have a pretty good picture, and so a number of us really started to get interested in trying to constrain smaller than present ice elevations. And so we just saw talk from John. So we've also been doing kind of similar things. Just again, a quick review. These mountains that stick through the ice sheet, you have a lot of weathering, you have erratics, you can determine where the ice sheets were in the past. And then the motivator is, for almost everyone in the room here, is what did WAIS do in warmer climates, and what is it as analog for what it might do in the future. So in this, oops, we go back here. So I'm going to be talking about the Ohio range, which is right about there. Present ice, a snapshot of one of the collapse events from Bali to Congo. So while it's universally accepted that the ice sheet has been small in the past, all of that data is far field sea level for information, which is the water had to come from somewhere. And until very recently, the only data from on the continent is this work, back in the day by Weed, where they found diatoms in Burlington under the ice sheet. So what we're trying to do is add to this very sparse data set. And the way we can do that, as we've seen already, is by drilling through the ice sheet and looking for evidence of past exposure using cosmogenic nuclides. So I'm going to be talking about the Ohio range. And then, just as a schematic, the idea is, these little stars are supposed to be more or less cosmogenic nuclides. You work your way down a profile. You'll eventually get to a point where the ice is never left, and you have none, and then a changing, increasing concentrations above that. So just to show where we are, here's the Ohio range at the end of sort of the last outcrops of the Transantarctic Mountains, near the Waste Divide, the headwaters of the Mercia ice stream. And we're motivated to go back here because we've done a number of field seasons, and we know quite a bit about the area. It's already been mentioned, there's a trim line here at about 125 meters above present. And then there are, and that was about 10,000 to 12,000 years ago, showing this early Holocene maximum derived from increases of accumulation. And there's also these nunataks here and here, and this is a blue ice ablation area. So what do these nunataks look like is this. They're very weathered granitic rocks that are lower than the trim line. So all of these things, they show extensive rock weathering, but they are covered with erratics that indicate recent cover by the ice sheet. We've looked at the bedrock above the ice sheet before, and this focus on actually these two samples. So we have millions of years of exposure on the peaks of those nunataks, this field in the diagram here is the area which is called simple exposure. You can get data in these points just by having a rock exposed over time and ingrowth of cosmogenic nuclides with reasonable erosion rates. If you have two nuclides, you can actually get both of those things. But so that's sort of the background of what the bedrock looks like. And then you can take these models which we've already seen from example Pauly de Canto, calculate what the predicted exposure of the model is and test the model. What can you get there from there, so to speak? And so we did that, and it turns out picking reasonable start times and reasonable erosion rates, the model, the 2009 model, actually you can get to one of the samples, but not the other. But if you play around with your elevation of your site, which is a kind of a cheat kludge to like lowering the ice sheet, we could also reach both of those things. So the Pauly and the Canto model was looking very good from the actual evidence we had predicting the last high stand in timing and elevation, and then in the long-term sense, it was doing a good model for the peaks of these nunataks. So then you can go and predict what you would expect at the ice level and below the ice. And this is basically our proposal to go back and get samples from below the ice. So we did some site survey. It takes quite a bit of time to make sure you can find a place that makes sense to drill. This is just one of the examples that Seth Campbell produced for us. He did over like 700 kilometers of line, so you understand the bedrock topography at large and small scale at the site. So you can actually see this is the little ridge coming off of the edge of this nunatak here, based on some of these lines. And this is just some raw data that we work with. So we have this nice ridge, and then we can look to make sure we have clean ice to drill through and depths that we can reach. And we successfully used the Winky drill to retrieve cores from up to 30 meters below the ice. So that was a success in the first application of this new Winky drill. So just to show where we are, these are these two nunataks that are the nunataks that we were interested in. We have 4 successful cores, 2 of them off of this larger one we call Bennett 1, and 1 off this one that just barely emerges. These the ice around these things is kind of complex. We have moats and so forth, but again, the weathered bedrock right up to the edge where you work. This is a weathered bedrock from the crevasse, so we were pretty confident we would get cosmogenic nuclides. And to get to the meat of the talk, we have a spallation profile in the bottom of all these from these cores, so we know we have recent we haven't had exposure of the samples, so that was great. And then looking up in these banana plots, now instead of falling within this area, they're clearly, a number of them clearly below that. And this is actually the sort of the money plot. So you can look at our results in terms of like a simple 2-stage model to get durations of exposure. So these lines here are exposure, so we have, you can't really go. So this is 200,000, 500,000, 2 million here. So quite a range of exposure in the samples, all at about the same elevation, about 26 meters below the ice surface. And then these curves show how much cover you need to decay down to these areas. And interestingly, they're all very, very similar, within measurement error. And I think the simplest interpretation is you can use this sample and say, okay, we had at least several hundred years of exposure, and then several hundred years of alternating cover, and you could get all of these samples, but just by sort of starting an initial concentration about 500,000 years ago. This is just again that prediction for what we would get, and in this case, the model is under-predicting or over-predicting the amount of ice cover, which was consistent with our earlier measurements from above the ice. So just kind of graphically, this is a time with the predicted ice elevation history, and to get that amount of it, roughly half of the last 500,000 years being exposed, the site has to be exposed more than just in these major deglaciation type events, but actually during most of the glacial cycle. So the actual exposure time history of the site, this line has to dip down below this much more frequently. So to wrap it up, bedrock at roughly 28 meters below the present ice level has clearly been exposed to cosmic rays in the past. And we can say something that over the last several 100,000 years, it's been roughly half, which is much more than predicted by the ice sheet models, but consistent with other evidence that the ice sheet was actually thinner prior to the early Holocene. And then on the long term, the bedrock was mostly exposed, which is actually also consistent with these longer term glacial models. And then just for future, we just have literally scratched the surface here, and we could definitely stand to go back here and go deeper with OSE or bring in ACPL and go 700 meters. Thanks.
You want to stay on up here, and all the authors coming up, we can start our discussion. So we have until 10:15 to ask all of the questions of all the speakers. I'll just remind everyone what was covered. So Lindsay, our first speaker, shared some data from Marguerite Bay and the association of subglacial meltwater with grounding line retreat. Perry shared with us thickness of West Antarctica through the last deglaciation. Ryan, some cool mud from beneath the ice. Let's see, John and Trevor, both subglacial evidence of past WAIS collapse. And then Robert, of course, just shared results from Ohio range. So I'll keep an eye out for anybody's questions, and let's have a discussion and questioning of the speakers.
Can I make a prediction? I predict there's going to be an earthquake at 10:17.
Yes, we will stick to time, so as soon as we're done with this, we'll do the drop, cover, hold.
I can make for questions, I guess.
Yeah, and you can pass that around them.
Are there any questions?
Lindsay, I came in a little bit late, so I might have missed it. But I saw that you were showing some retreat that looks like happened from a shelf edge position to maybe middle or inner shelf before 14. Yes or no?
Yes.
Okay. And what do you think was driving that?
Well, I will say that we still don't know exactly when that retreat happened. So the work that was published in late 80s, early 90s on those cores, the ages from those cores were not from very deep in the core. There are minimum ages, and we actually haven't managed to get any definite constraints on those either. So that is just an estimate. So I can't really say for sure what was driving the change, because I don't really know when it was.
It could have been earlier.
Could have been earlier.
Yeah. And what about Heroy Anderson? Did they have any good dates for a little deeper? Or? It's been a while since I read that paper.
I've scoured all of the literature.
Yeah.
I haven't been able to find anything that's a really high quality.
Close to the transition.
Yeah.
Okay. All right, thanks.
So my question is for Ryan. I missed if you said you had an estimate on the number of pass filling draining cycles in Mercer Lake. So if you could say that again or speculate maybe.
So you're right that I didn't quantify that, but it's 7 based on the wiggles that I was showing. We definitely need to do a little bit more high resolution like image work. That's just looking at the CT scans. So we can track that back in time and assume that maybe the last 2 overlap with the instrumental record and kind of hand wave about how long that's been, but I definitely don't have a constraint on how far yet. Does that answer your question?
Yeah, and can you say again what the wiggles actually were? I got really distracted when I saw the time series.
No. So I was showing density changes from the CT scans in the core. And the lighter colors are the more dense material, and the darker colors that you were seeing were the less dense. So interpreting the less dense material as a thicker water column and having time for the finer grained material to settle, and the coarser grained material being left behind when water is moving through the system or water is draining.
Okay, cool, thanks.
Yeah, I also had a comment on that, and I was, I think you could imagine, maybe just the opposite situation of how you interpret it. But it seems like, looking, if you look at it in real detail and see which way it's finding, you should be able to answer that question.
Yeah, that's
So we might require micrographs or something if this, we're looking at it. Hopefully we can find that.
Yeah, that's a good point. We can discuss that
I have a question to follow up on that. So the way that you've interpreted those layers, the coarser ones being indicative of some flushing, what's the potential for complete flushing of the laminated deposits?
Yeah, that's a good point, and a good follow-on to Lindsay's talk too with the subglacial flow deposits. We did measure current in the lake, or tried to measure current in the lake, and there isn't very fast flow while it's draining. So that's something that I should have mentioned, is that during the time that we sampled it was during a draining event. And there's no noticeable current. So I guess to answer your question, I don't know what the chance of getting rid of everything in. I think you would need a pretty high flow outburst kind of event to happen.
I have a question for Trevor, which I asked Robert Ackert a second ago, so he might want to respond to it as well. But you mentioned that to get collapses in this ensemble, you kind of have to crank all the dials up, and in particular the basal traction. What have you thought about? What I'm surprised that you get more collapse when you increase that. Do you have any comments on that?
Yes. So the mechanism there, I think, is that increased basal traction allows a really thick ice sheet to grow up during glacial periods, and then if you have a slow rebound time scale, the bed just doesn't pop up to stabilize as the ice sheet retreats.
Cool. That was Robert's answer as well. That makes sense. I just want to note that I've been doing some work trying to use the same model to make sense of the ice cores, and you really need stronger basal traction to make any sense of the ice core records.
Oh, interesting.
However, my results possibly contradict Robert Ackert's results, so there's more to figure out there.
Hi, this is a question, I guess, maybe for Trevor. I noticed on some of your model runs, some of the ensembles seem to respond very weakly or not at all to MIS 5e and MIS 11. And I know that my sense is that you probably throw those out because you know that there had to be some response. But does that give you a clue as to the extent or the thickness if some of the ensembles simply don't pick those up? Is that useful at all? It was interesting to me.
Yeah, I think for 5e, if I'm remembering correctly, I think some of those ones that don't seem to respond, that's actually because part of the model domain is within East Antarctica, and there's actually an advance of that part while the ice sheet retreats. For stage 11, there's a similar phenomenon in which the Ross Sea retreats and the Weddell doesn't in a few model runs. And that, yeah, it's anybody's guess as to what's right there.
So I don't think Sasha's here today, but he gave a talk at AGU many years ago that likely a lot of people in this room remember, where he started with the old parable of 5 blind men grabbing an elephant in different places and thinking it's a different animal. He had a stuffed animal, one we all remember. But I'm getting kind of a similar feeling right now where we have these great different techniques and they're all working in pretty different systems and looking at different parts of the system. Is there hope for projects that start combining these techniques, going from, hard bed down through the soft bed or tracking through a paleo flow line? What's the next step here to put it all together? Perry can start.
Well, I think from the subglacial bedrock recovery drilling, we do need more samples from multiple sites within the ice sheet, and importantly, from not just one sample at a given site, but over a range of depths to look at that. Combining with other studies, it's a little hard from using that technique, but I think a range of different techniques is important. So actually drilling into subglacial sediments. One of the nice things about bedrock is you can start from the surface and go down and you don't have to commit initially to a very large and logistically challenging drilling project. You can if there's evidence for past exposure down to the capabilities of the Winky drill, like 100 meters, that's possible with a relatively small project. And then if you find that evidence that might warrant future drilling. So I think that's one advantage of that technique. Others can speak more to this if they want.
Yeah, I was just going to say that I think that at some level, what we're doing like right now is where the integration is probably the most fruitful way to do that, as opposed to try to front load all of the different factors that you think you're going to need to make a comprehensive picture.
Just going to make the simple observation that deglaciations and collapses they're grounding line phenomena. So what happens at the grounding line and all the work that's being done at the grounding line is really informing the understanding that we hope to derive, we hope to see the results of as it moves into the ice sheet. Tying those two bits together, of course, will happen best when we can mesh chronology, and so really happy to see dating coming up or being done in the sorts of work that's going on in the Wizard and Salsa projects and Reed's work, so forth. And we hope to be able to see when we're looking at the same thing from two different places. Fundamentally, they can't be done in the same place, but we can tie them together in the long term.
Well, I think it's really exciting that there's so much work that's been done on Upper Reedy, and now we're on Lower Mercer, and we can start tying this together.
And so, while we're on this subject, I would point out to the people who are working on the Mercer Ice Plain down there that there are actually exposure ages from Reedy, Scott, there are carbon 14 dates from Amundsen, all the way up to Lib, which show that those glaciers were still thick up until about 3,000 years ago. So, particularly the original model suggestion model-based suggestion in the Kingslake paper that this happened 9,000 years ago is very flatly contradicted by exposure agents from essentially all transatlantic mountains out of glaciers at that time. But there is room perhaps to fit it in the very latest Holocene.
So my question's for Trevor. So you mentioned that the idea that the ice shelves were larger than present during some of your simulations. And is that a consequence of the calving front being further north or the grounding line being further south?
Actually, both, I think. But the big effect is especially in the Waddell sector, the model makes a really big filter around the ice shelf.
Yeah, it's kind of curious because it seems like it would be the grounding line because the northern extent of the ice shelves are always so closely tied to penny points, which are going to be consistent, in the same place. I'm thinking, Roosevelt and on the Waddell side there are these big possible penny points that should be reoccurring and really kind of limiting. You see what I mean?
Yeah, that does make sense. There are a few places that the model predicts ice shelves that we don't see ice shelves today. So, for instance, it has a large one in the Amundsen sector actually extending quite far into the...
With no apparent penny point.
Right, yeah.
Just another question, I think.
Just holler if I don't see you.
Yeah, this is for John. I mean, what is the thickness of local snow that you would need to sort of be fooling ourselves at Pirate Hills? In other words, let's say that because the ice sheet went away, there was no more katabatic flow, and so all of a sudden it became an accumulation zone instead of the blue ice area that it is today. I mean, this is kind of like a nightmare scenario. What would it take for us to be fooling ourselves? How much snow thickness can you, say confidently that there would have to been to explain the cosmogenic nuclides that you see?
Well, you have to honor the mean thickness constraint. You can envisage scenarios like that, but they then have implications. First of all, you have to find a way to preserve that old ice. Whatever ice accumulates over that cannot flush the existing WAIS old ice out, nor can it erode its bed. It can't be warm-based. It would have to, you would have to envisage a scenario where for millions of years that process was happening, and each time no rock got exposed. So effectively you're envisaging a world in which maximum rock is not at maximum warm climate. The simple-minded assumption is that as the planet warms, more rock becomes exposed. But you're envisaging a scenario in which at some point you reach maximum rock and then you start covering it up again. And so when you start thinking about that, you also draw in all of the work that we have done, and many other groups have done all around West Antarctica and into the Transantarctic Mountains, where there are records of very long, prolonged exposure, continuous exposure, effectively, for mountaintops. In the Pirate Hills, once you get above that 300-meter level that was affected by recent glaciations, the exposure ages jump to effectively almost saturated beryllium 10. which means that you have to keep those surfaces ice-free for very, very long periods of time. Way back into in fact, I think the record in West Antarctica is top of the Whitmore's, where there's a 14 million year beyond 21 age. But, so the scenario you envisage must also has implications for all of that. That you cannot simply add ice to West Antarctica without predicting you make a prediction about what we should see in terms of the burial of summit rock, which you could perhaps hide some of that in the existing data, but not much.
Just following up on a comment that John said, and speaking on behalf of the Kings Lake et al. Authors, we fully embrace the idea that it was a younger age. We took a rather broad view in that paper because we still had calculations to do, and some of the round pyrox that's been done, and some of the diffusion modeling that Sarah and Slavic have done are also pushing that toward a younger age. But we gave it the broad constraint starting at around 9. It wasn't particularly well constrained.
Yeah.
So I do not disagree with what you say at all.
No, not at all. And actually, that makes another interesting and illustrative point, which is clearly the Kings Lake. As far as I can tell, there's no reason why the ice rumples in the Weddell-Sea and the features that were described in that paper from the Weddell-Sea need have formed at the same time as the incursion in the Ross Sea. Yet the reason why they appear that way is because that model was driven by a climate model that drove synchrony in those two places, and the real ice sheet is just much more complicated.
Yeah, I agree with Sasha. Elephants have many parts.
Yeah, exactly. And so, that's a really good for all of us to embrace, is that we shouldn't expect simple behavior here. We should expect complicated behavior. And so let's all keep working at it to see how we can.
But interestingly, in the Albrecht and Rees run of PISM, not much happened in the Amundsen Sea embayment during that entire sequence, and that's a interesting and potentially very important part of the puzzle. And I'll touch on that a little bit in my talk this afternoon.
Okay, I think we're going to have to cut it off there. So if we could thank all of our speakers again. We have a coffee break and a